I'll now go over question 3 on exam 2. Question 3 is stated as follows. A box of mass 10.0 kilograms is sitting on the edge of an unbanked merry-go-round of radius 4.00 meters. If the coefficient of static friction between the box and the merry-go-round is mu sub s equal to 0.6000, part A, draw the free body diagram of the box. Well, let's do that. Here is the body, and horizontally there is a force acting inward, causing it to change its direction and to continue to go around in a circle. We identify that force as the static friction, and it is the only horizontal force acting on the object, and is the source of its centripetal acceleration. It is the centripetal force. There is no force acting in the opposite direction. Acting vertically, we have a weight acting down, and we have the normal force balancing it, acting up. Okay, so that's part A, worth 1 point. In part B, what is the magnitude of the force of friction? S of friction, which I called S of S in my diagram. What is that magnitude between the box and the merry-go-round if the merry-go-round is moving at a speed of 3 meters per second? Well, the friction force is, as I said, the centripetal force acting on the object. So it causes it to have a net force equal to m times a, where a is the centripetal force, its centripetal acceleration, which we know is equal to v squared over the radius. So to calculate the friction force, we just calculate m times v squared over r. So we put in the mass, which is 10 kilograms, the velocity, they tell us, is 3.00 meters per second. We're going to square that, and we're going to divide by the radius, which they tell us is 4.00 meters. Then when we calculate that, we find that the S of S is 22.5 newtons. Okay, that's worth 3 points. Part C, find the period of the merry-go-round. Well, we know the velocity. It's given, and we know the radius. And we know an object undergoing uniform circular motion, as this one is, has a velocity equal to the distance around one revolution, 2 pi r. divided by the time for one revolution, which is the period. So this means that the period is equal to 2 pi r over the velocity. So we put in the numbers. The radius we said is 4.00 meters. And the velocity is 3.00 meters per second. The meters are going to cancel out, and the seconds are going to go up in the numerator. So when we calculate this, we get an answer of 8.38 seconds. So that's 1 point. Part D. What is the frequency? Well, the frequency is simply the reciprocal of the period. So this is equal to 1 over 8.38 seconds. And we put that in our calculator, and we see that is 0.119 seconds to the minus 1, or revolutions per second. That's worth 1 point. Part E asks, will the box slide when the merry-go-round is going this speed, yes or no? Find the magnitude of the maximum frictional force, F max, that the box can have before it starts to slide. And this will tell us whether it's going to slide or not, because we know right now that the friction force that's being exerted is 22.5 newtons. As long as this force is less than the maximum static friction force, then it will not slide. So let's calculate this. S of S max, or F max, is equal to mu sub S times the normal force. And we know from the free body diagram in part A that the normal force is equal to mg. And they tell us that mu sub S is 0.600. The mass is 10 kilograms, and G is 9.8 meters per second squared. So when we calculate that, we see that that's 58.8 newtons. So since the friction that we are experiencing right now, 22.5 newtons, is less than the maximum friction, then it will not slide. The answer is no. In part F, the question is posed, if the box did slide, which direction would it move? Briefly describe its motion in words or a picture. Well, if we look at what's going on from above, Here's the merry-go-round as seen from above. And let's say it's rotating in this direction, counterclockwise around an axis going through the page. And say at this particular instant, it slips. Well, it's the same thing as if it were tied by a string, exerting a tension T, and it would suddenly just break. Well, the object would just continue moving off with the velocity it has at the instant of the slip. So it will continue in this direction. Tangential to the merry-go-round at the instant of the break. So the path it will take will be along this line. It will not go in the opposite direction of the friction force, nor will it go inward in the direction of the friction force. And that concludes this question.